Thank you for joining us for this display matching presentation. My name is Brahm Desmet, and I'm the CEO and General Manager of Flanders Scientific. Our goal in this presentation will be to introduce the key concepts involved with the challenge of display matching, especially as it relates to matching displays of different technology types. When it comes to matching two of the same exact model display, the process is usually pretty easy provided that there are sufficient calibration controls on the monitors. Our goal in this process is to have the displays give us the same color and luminance output for all given test patches. When we achieve this, we can expect a perfect visual match between the displays. It's not enough to match just a single test patch like white. What we really need is all aspects of display setup to be equal. On professional displays with 3D-based calibration support, this is particularly quick and easy as you can calibrate both displays to the same standard using software like Light Illusions Lightspace or SpectralCal's CalMan that largely automate the calibration process. Calibration can become a bit more involved of a process if trying to match different monitor models, but if they utilize the same or similar display technology, a visual match should still be possible by simply calibrating the displays to give you the same color and luminance output for all given video levels. But what exactly do we mean by similar display technology? Is it enough for the displays to be from the same manufacturer or have similar technical specifications? Unfortunately not. The one defining characteristic that really lets us know how similar the light output from two displays will be is the spectral power distribution of the displays. Identical or closely matching spectral power distributions let us know the light output from the two displays is for all intents and purposes the same. In this example, you see Flanders Scientific's CM172 and CM250 OLED monitors. Even though these units are not exactly the same model, they both still utilize the same type of RGB top emission OLED technology, providing for an exceptional visual match as they have identical spectral power distributions. If you're new to this topic, you may be asking yourself, what exactly is spectral power distribution? Well, it is a measure of the amount of spectral energy emitted by a light source at each wavelength within the visible spectrum. Spectral power distribution is akin to the fingerprint of the display technology in question, and every display type has a unique inherent spectral distribution. Here you'll see some examples of popular display technologies and their corresponding spectral power distributions. You can see just how widely these vary. Even among similarly named display technologies, variations can exist. For example, here are two types of OLED displays. Despite the similar name, you can see that the WRGB OLED on the left has a drastically different spectral distribution than the RGB top emission OLED on the right. So as mentioned, calibrating two displays with the same or similar spectral power distributions to match one another is not difficult. But how can we expect to achieve a match if the spectral distributions between two displays are so drastically different? This is where the concept of metamerism comes into play. Metamerism is a scientific concept that a visual match between light sources will be obtained when the spectral power distributions in question result in the same total light absorbency by each of the sets of cones in the average human eye. To better understand this concept of metamerism, we need to take a bit of a closer look at how human color perception works. The typical human eye consists of light-sensitive cells called rods and cones. Rods provide us with low light sensitivity. Cones provide us with color and detail. The majority of humans are what we call trichromats, which means they have three types of cone receptors. With trichromatic vision, each of these three types of cone receptors has a distinct pigment that allows varying degrees of light to be absorbed by the cone receptor at any given wavelength. This is a bit oversimplified, but if we look at the typical response of the cones, we can break them up into what are called short wavelength or blue sensitive cones with a peak light absorbency around 445 nanometers, medium wavelength or green sensitive cones with a peak light absorbency around 535 nanometers, and long wavelength or red sensitive cones with a peak light absorbency around 570 nanometers. In 1931, the International Commission on Illumination, more commonly known by its abbreviated French name CIE, made its first attempt to more precisely define the spectral response of these cones. The spectral response curves defined by CIE in 1931 were based on the independent experiments of William David Wright and John Guild in the late 1920s. The data was averaged and presumably based on observers with normal vision. This then became the basis for what we call the standard observer. It goes beyond the scope of this presentation, but it is important to note that even in the early 1900s, it was understood that the field of view had an impact on color perception. A 2-degree field of view was selected to help neutralize this variable, and that is why the standard observer model is often referred to more completely as the CIE 1931 2-degree standard observer. The CIE-defined spectral cone sensitivities can be mapped to any of a number of different color spaces for practical applications. CIE XYZ is one such color space and was devised by CIE to accomplish a long list of pragmatic goals, including among other things tying the Y stimulus component to luminance and avoiding negative numbers for any of the tri-stimulus components. CIE XYZ encompasses all colors that can be observed by the standard observer and is therefore device independent. In other words, all colors that can be produced by any given display device will be within the bounds of CIE XYZ. There's a lot more that can be said about XYZ, but for our purposes, the important parts are the resulting color matching function and CIE XY diagram. The relationship between the standard observer's spectral sensitivities and the CIE XYZ tri-stimulus values is called a color matching function, or CMF for short. The basis for the vast majority of current video display device color standards is the CIE 1931 2-degree standard observer CMF. CIE XYZ is properly modeled as a 3-dimensional color space. However, for easier 2-dimensional visualization, a CIE XYY model is typically used where big Y represents luminance and little x and little y represent the 2-dimensional chromaticity plot on the CIE XY diagram. Big Y, or luminance, is easily found as the Y value within the XYZ tri-stimulus data. XY chromaticity values are derived from the equations little x equals big X divided by big X plus big Y plus Z, and little y equals big Y divided by big X plus big Y plus Z. The luminance value is not shown directly on the XY chromaticity diagram, but the big Y value is often reported alongside the chromaticity data in any numerical representation of the color in question. While CIE XYZ and the 2-degree standard observer CMF are at the heart of most current video display standards, the actual target values specified by these standards are more often than not the derived CIE XYY values. For example, SMPTE Standard 2080 specifies reference white as little x equals 0.3127, little y equals 0.3290, and big Y, or luminance, equals 100 candelameters squared. This brings us full circle to the concept of metamerism we mentioned early on in this presentation. When two different spectral distributions appear visually identical to an observer, they are considered metamers. When two displays produce the same CIE XYY values, they should in theory be metamers. But here's where things get interesting, because in point of fact it is quite common to have two displays with different spectral distributions yield the same XYY values and yet not visually match. When this happens, we can classify it as a type of metamerism failure. A quick aside here before we move on. It is important to mention that in fairness to the professional color scientists of the world, we are using the term metamerism failure in a somewhat less classical sense of the phrase as it applies to abstract color science. An argument could be made that what we are describing is in fact a type of observer-dependent metameric failure, but as you will see in just a moment, our issue is really with the color science model in use, so more academic definition of the problem might avoid the term metamerism failure altogether. However, for our purposes, I think it is appropriate as we are discussing a theoretical condition in which metamerism should, but fails to exist, so by all accounts metamerism failure is not an altogether unreasonable phrase to use. It's important to distinguish the display matching challenge we are discussing here from display matching difficulties caused by inadequate measurement devices. For example, a low-quality measuring device may indicate a CIE XYY match even though higher-end measuring devices may clearly show that the XYY values are not the same between two displays. Even with high-end colorimeters, the failure to employ proper spectroradiometer-determined display-specific matrices can lead to erroneous readings. While these are real-world considerations that can further aggravate display matching efforts, they do not explain away the metameric failures that still occur even when using extremely accurate measurement devices. Instead, the fundamental issue is the CIE 1931 standard observer model's inability to accurately predict metamers with today's diverse display devices. Knowing that CIE 1931 often fails to provide us with adequate matches between display devices, you may be asking, why is it still used? As it turns out, it has been difficult to devise a substantially better color science model. Attempts at this have been made that took into account new experimental data, different fields of view, and so on, but the improvements have historically been considered too marginal to completely upend existing standards and practices. A part of this is that observer variability does actually make defining a single effective standard somewhat difficult. The distribution or ratios of the types of cones in the eye, inherent cone sensitivities, and age-related discoloring of the eye are variable from observer to observer, meaning we tend to perceive color slightly differently. That notwithstanding, with the move from the predominant use of CRTs to the wider variety of display technologies in more recent years, we've started to see some adoption of alternate color science approaches to aid in specific display matching efforts. The CIE 1931 2-degree standard observer color matching function is not the only CMF available to us. Many alternate CMFs have been devised over the years in an attempt to improve upon the shortcomings of CIE 1931. One particularly popular alternate CMF that has seen fairly wide-scale adoption with users of some display technologies is the Judd-Voss modified CMF. This color matching function tackles a specific shortcoming in CIE 1931 dealing with the spectral response in the short wavelength region of the visible spectrum. In display devices using a primary with significant energy below 460 nanometers, the Judd-Voss CMF can provide a better match to other technologies. This CMF is most commonly used with OLED displays. While the consensus seems to be that Judd-Voss works much better than original CIE 1931 CMF at getting OLEDs to at least look more similar to other technologies, experience has taught us that it by no means perfectly mitigates display matching failures or challenges. The use of alternate CMFs also poses at least two interesting challenges. First, the majority of measurement devices are set up to report values based on CIE 1931 CMF and not alternate CMFs. Some measurement devices may support or be built upon an alternate CMF, and software can also potentially convert from one to the other, but this is not the norm. Second, display setup standards still reference values based on CIE 1931 XYY. The common solution to these challenges, as it specifically relates to OLEDs in the Judd modified CMF, is to convert CIE 1931 XYY values specified by a given video standard into a new set of CIE 1931 XYY values that are equivalent to the modification implied by the alternate color matching function. Ultimately, this allows you to simply use existing equipment to calibrate to redefined XYY target values. The use of alternate CMFs has seen recent validation by way of specific mention or incorporation in some of the most recent video display standards. Alternate CMFs may offer an improvement upon CIE 1931 CMFs, but in some facilities where different display technologies share the same space, an even more effective display matching method may be desired. Luckily, there's a perceptual color matching workflow that tends to offer superior results to just about every other available option. The process is relatively straightforward. First, we must select which one of our devices will serve as the primary reference. In a post-production application, this is usually the primary grading monitor to be used by the colorist or editor. This primary reference device should be calibrated as normal to an objective standard. The second step is to perceptually match the secondary device, for example a client monitor, to the reference display. If your client monitor supports 3D LUT-based calibration or is used with something like an external LUT box, this process is easy when coupled with calibration software like CalMan or Lightspace that allow for custom targeting when building a LUT. We have a more detailed white paper on this process available at flandersscientific.com, but the basic premise is to generate a static white or gray test pattern on both the reference display and secondary display. Then you manipulate the white balance on the secondary display until it visually matches the reference. It's important to make sure that manipulations only impact the secondary display and that the reference display stays unaltered. FSI, as well as some other brands, offer a freeze or still frame option that can help with this and allow you to make adjustments more conveniently from your color grading software as opposed to having to use the white balance controls on the secondary display. Once you achieve a visual match, you measure the XY values on the secondary display and use this as your new target when building your calibration LUT for the secondary display. This will provide you with a weighted perceptual match to your reference display that still ostensibly calibrates your secondary display to a defined specification. Perceptual matching of displays can work quite well, but it does have some limitations worth considering. The most obvious limitation is that due to observer variability, the perceptual match may be perfect for one observer, but not the other. No amount of color science is going to resolve that particular challenge. Only using displays with the same exact spectral distributions will afford a perfect match between displays as seen by all observers. The other limitations to consider all have to do with the relative performance of the displays in question. You can make the greater contrast and or wider gamut display match the more limited contrast or narrow gamut display, but not vice versa. For most users, if decent color matching can be achieved, then usually things like contrast differences are not too objectionable. But if there is a very wide variation in contrast capabilities, then you may want to consider intentionally limiting the contrast of the better display a bit for an even better perceptual match. Other differences like viewing angle performance and display uniformity are more difficult to account for, and this is where proper product selection and room design can be quite helpful. It should be noted that while display matching can be a complex topic, it is also easy to overstate the significance of this challenge. The issue of display matching primarily comes up in scenarios where different technologies are used in the same viewing environment. In those applications, the potential workarounds we have discussed can be helpful at improving display matching. However, in applications where various display technologies are used, but not in the same exact viewing environment, nothing further than normal calibration to an objective standard is usually needed. The reason for this is that the human eye is a very good relative measuring device, but a rather poor objective measuring device. In other words, if you put two displays right next to each other, the average observer can spot even very small differences between them. However, you put those displays in separate rooms, the differences usually have to be fairly significant before they become noticeable or objectionable to an observer moving from one room to another. Finally, given all that we've learned on this topic, there are a few room setup considerations that we can review. First, some facilities have transitioned to single monitor viewing environments where the colorist or editor's primary grading display is the same display the clients are viewing. This obviously eliminates any display matching worries, but does not work in all rooms, nor do all operators feel comfortable in this type of setup. Another popular setup is to move the colorist's primary reference display out of the line of sight from the clients in the room. This mitigates any display matching issues for client viewing, but again, it is not a one-size-fits-all solution. If you're faced with a situation where display matching is a concern, I hope this presentation has provided some useful insight as to the underlying causes of display matching difficulties, as well as some helpful tips to work around these difficulties. Do you have other topics or questions you'd like to see us cover? Let us know by emailing vlog@flandersscientific.com. To learn more about Flanders Scientific and the products we offer, visit our website at flandersscientific.com. Thank you for joining us.